Section 6.1. Suppose dy dx is some function containing both x and y, and you're given an initial condition, x at a equals b. You want to approximate x at some other value, we'll call it c. What we're going to do in section 6.1, we're going to learn a method for approximating solutions to differential equations. This will be Euler's method. Section 6.2, we'll learn a different method for approximating solutions to differential equations. And then section 6.3, we'll learn yet another method for approximating solutions to differential equations. Why do we need three different methods?
Because one doesn't work.
No, they all work.
Because variety is spice of life. Because variety is purple.
Why would you, okay, that's an excellent question. Why would you need to approximate the solution to a differential equation?
If there's no real solution.
Well, there is a real solution.
Because we're going really, really fast and we just want to check it. Walk it around here.
Because it's quick and dirty.
It's quick and dirty. All right, so let me ask you a question.
Yes.
It's definitely
Could you solve that differential equation exactly? The correct answer is yes. Yes, yes, we can. The correct answer is yes. What kind of differential equation is that? That is not separable. Which kind of differential equation is that? It's first order linear. That is correct. That's a first order linear differential equation. You can solve that equation exactly. In fact, in a few minutes, we're going to solve that equation exactly. Could you solve that equation exactly?
No.
The correct answer is no. I cannot. But using the techniques we're going to learn today, we can develop approximations. So what happens in real life? In real life, quite often when you're dealing with differential equations, the functions that get involved get quite ugly. So solving exactly becomes very, very difficult, if not impossible. So quite often the reality is you approximate a solution. And that's good enough.
You just leave it to Wolfram
Type that into Wolfram Alpha. I'd be willing to bet it can't solve it either.
Oh my God.
Give it a try. Challenge for Wolfram Alpha. I bet it cannot solve that differential equation. I'll be at a computer right here if you really want to try. But
I'll come back tomorrow.
I'm pretty confident Wolfram Alpha will not solve that differential equation. I'll go try it afterwards just to make sure. Anyway, so why do we need three different techniques? Well, it's kind of a historical thing. Euler's method was the first technique developed. It's also the easiest. Not surprising, yeah, Euler did everything. It's also the easiest to use. The downside is, no, it doesn't take longer. Well, yes and no. It's the least accurate. So if you want a more accurate answer, you have to do more calculations and it takes longer. So that's what we'll do in section 6.1. Section 6.2, Euler liked his method, but he didn't think it was great, so he improved it, and he came up with Euler's improved method.
I'm so done with Euler.
You is not satisfied with his achievement.
He was not satisfied with his achievements. He kept going. And so section 6.2 will learn a different technique for solving. The advantage of it is it converges more quickly. The disadvantage is there's a little bit extra work at each step, and we'll see that. And then the third method, Rutekunga, I believe it's called, a couple of Indian mathematicians, I believe, was developed in the 1900s sometime, 1930s, 1940s, I want to say, somewhere in there. And the advantage of it is it converges very, very quickly, But once again, you'll see there are significant calculations at each step that you need to do. It gets harder and harder, but from a computer programming standpoint, it runs faster. Because where for Euler's method, to get an accurate answer, you might have to do 20 iterations, which means a lot of calculations. For the Rutikanga method, to get the same degree of accuracy, you might only have to do 3 iterations. But there's more work to do for each iteration. But the overall programming is faster. So from a computer programming standpoint, the Rutikanga method is the most efficient. You get the most accurate answer for the least amount of calculations. If you're doing it by hand, it's the hardest method to do. So we'll see. Anyway, Euler's method says, suppose dy dx is some function in x and y, and we know we have an initial condition. And we want to approximate at some other spot. What you're going to do, you're going to decide how many iterations you want to do. Pick n, which is the number of iterations. Then you're going to have c minus a over n. We're going to call that h. And so here's the general idea. We did this in Calc 1 all the time. We're starting at some point A, we're ending at some point C. And we're going to decide how many intervals we want to create out of this one interval. So maybe, for example, maybe we want to do 4 iterations. So this distance would be h, and how big would that be? It would be c minus a over n. So you take the length of c minus a, you divide it into 4 equal subintervals. So what define n? N is defined by you decide how many iterations you want to do.
Oh yes, this is the number of...
N is the number of intervals that you want to create. And then in calculus, we always called that distance delta x when we were taking Calc 1. And we made delta x smaller and smaller. When delta x got smaller and smaller, our answer got more and more accurate. Same thing happens here. The more iterations you do, the more accurate your answer will become. Okay. And then there's simply a formula for creating the next y value. Y sub n plus 1 is going to be y sub n plus h times f at x sub n comma y sub n. Okay, so all this says is to compute the next y value, you take the current y value and you add, you multiply by h. What was h again? The length of the subinterval. And what's this? It's the function, but what is the original function? The original function is equal to the derivative. So we're computing y by taking our current y value and adding a multiple of the derivative. After all, what does the derivative tell you?
Rate of change.
The rate of change, which is the slope, which is change in y over the change of x. So we're taking the change in y over change in x and multiplying by a change in x, multiplying by delta x, basically. All right, so we're going to take this y prime equals x plus y. And x at 0 equals 1. We want to approximate y at 1. How many iterations of Euler's method do you wish to do?
2.
0.
0 is how many I wish to do. How many am I willing to do? You want to do 5?
All right, 3 sounds good.
Let's start with 2. Let's start with 2,
Come on, guys. We got like...
and then we'll jump it up to n equals 5, and we'll see what happens. So we're starting at 0. We're ending at 1. if we're doing 2 iterations, how big is h? 1/2, because it would be 1 minus 0 over 2, which would be 1/2.
And it should always be a positive, right?
It's just a distance, yeah, it should always be positive. So you always take the big number minus the small number, divide by how many you want. All right, what I like to do is build a table here. I'm going to have n, x sub n, and y sub n. When n is 0, x sub n is 0 and y sub n is 1. That was the initial condition given to me. So 0, 1. When n is 1, what's my x value going to be? Well, I start at 0, and how big a step do I take each time? 1/2. So if I start at 0 and I take a step of 1/2, I'm going to have 1/2. And when n is 2, when I'm all done, it would be 1. I started at 0, I stepped up by 1/2, I stepped up by another 1/2. Well, we've done the easy calculations so far. Now we got to do the harder calculations. All right, so to compute y sub 1, I have to take y sub 0 plus h times f at x0, y0. What was y sub 0? 1. Plus, what was h? 1/2. And f at x0, y0. That's x plus y, and x0 was 0, and y0 was 1. 0 plus 1.
Wait, how is y? So y is 0 equals 1. H is 1.
Okay?
And then 0 plus 1.
Because to compute the next y number, we take h, which was 1/2, and then we plug in x and y into our function. Our function is x plus y.
Oh,
So I plug in 0 plus 1. All right, so I work that all out, and I get 3/2. All right, now let's compute y sub 2. Y sub 2 is going to be y sub 1 plus h times f at x1 comma y1. What's y sub 1? 3/2. That's what we just figured out. Plus, what's h? 1/2 times.
0 plus 1.
Not 0 plus 1. 1/2 plus 3/2. To compute the y value, you always use the previous x and y values. So that's 1/2 plus 3/2. 1/2 plus 3/2? 4/2, which is a fancy way of saying 2. 2 times 1/2?
So y2 equals 5/2?
So that's 5/2 when you add it all up. 5/2. So our approximation is x at 1 is 5/2.
How really cool.
Hold it.
Okay?
Okay.
George, is there a limit to the precision you can get to these 100,000 and 10?
The more you use, the better your answer will be.
There's no limit to that?
Nope. So let's do the same problem again, except now we'll do more. Y prime equals x plus y. X at 0 is still 1. And we want to approximate x at 1. And this time we'll go with Jesse's. This time we're going to create 5 intervals. If we create 5 intervals, How big is H?
I don't think we should do this problem anymore. The universe said no.
Ghosts are angry.
Ghosts are angry, not just a wind slamming a door closed. That's all it is. 1/5. H is 1/5. Okay, so we're going to have n x0, y0. We're going to have a 0 there. 1, 2, 3, 4, and 5. What's x0? 0. What's x1? 1/5. What's x2? 2/5. Next one? 3/5. 4/5. And finally 5/5, which is 1. So the x's are very easy to fill out. It's the y's which are not so fun. The first one's fun. The first one is 1. All right, so to compute y sub 1, we take y sub 0. How much is y sub 0? 1. Plus our h value is 1/5. And then we plug x0 and y0 into our equation. 0 plus 1? That's 1. So what's 1 plus 1/5? 6/5. All right, 6/5. To compute y sub 2, we take y sub 1, that's what we just figured out, that was 6/5, plus 1/5 times, I take x plus y, so that's 1/5 plus 6/5. What's 1/5 plus 6/5? 7/5. 7/5 times 1/25. I'm sorry. I gave it away. That's 7 over 25. Get a common denominator and add, you get 37 over 25. Beautiful. All right. 37 over 25. It's going to get ugly. Well, we'll see. Y3 is. We take our answer, 37 over 25. We add 1/5 times x plus y, because that's our equation, x plus y.
Change it to 10 over 25 plus 37.
It's going to be 37 25ths plus 2/5.
Wait, why is that?
Oh, yeah.
X plus y, that's 2/5 plus 37 over 25.
Oh.
Which is
232 over 125.
232 over 125 is the total answer? 232 over 125. Okay. We keep going. Y sub 4 is our previous answer, 232 over 125, plus 1/5 times, I plug in my previous answers into my equation, that's 232 over 125, plus 3/5. Here, clickety clickety, so I'm waiting for somebody to give me the answer here.
So it should be 1785 over 625
1785
over 625.
over 625. Anybody agree?
Feels right.
Yeah, I got 1467 over 2 or 625.
You got what?
1467 over 625.
1467 over 625?
1467.
2 people got the same thing? 1467 over 625. Okay. And finally,
Oh yeah, you're right with the 14.
y sub 5 is 1467 over 625 plus 1/5 times 1467 over 125 plus 4/5 over 625, yep. Wait patiently for an answer. Say it again, please.
9,302 over 3,125.
Give me a decimal approximation.
2.97.
What is that?
2.976.
2.976. Okay. How good is that answer?
Well, that answer would have been 2.5. So, yeah.
Well, this one would have been 2.5.
This one's approaching 3.
This one's bigger. Is bigger better? The more iterations, the more accurate. That's correct.
How many iterations do we need to do on the test?
How many iterations would you need to do on the test? No more than 20. Yeah. On a test, I think reasonable would be maybe 4 at most.
So if you program like this, you know, how many iterations can you just do that?
What's that?
If you write a program, you just run these iterations. It's super easy to program.
If you write a program, what would you call it? Euler, maybe?
Yeah.
You have, I was a,
Oh,
we should go on things.
And we want to do 5 steps. And we want to start at 0. And we want to 1 and 1. Hey, look at that.
I guess someone else already did it. Okay.
Sure.
Why'd you say it like that?
2 weeks from now, I'd be more than happy to give it to you.
Oh.
George, what did you put 10,000 for the number?
What if I put 10,000 in?
Do it by hand anyway, so it doesn't matter.
No way.
We'll come back to this. It's going to take a little while, as you can see. Let's solve this equation. Let's solve this equation exactly. Of course, having it printed each step slows it down. If I didn't tell it to print, that would be faster. But
Wow.
let's solve this exactly. We decided this was a linear equation. So linear, we would usually write it as y prime minus y equals x. We noticed it was linear because it had a y prime and it had a y to the 1, and it did not have a y to another power. If it had a y to another power, it would have been a Bernoulli equation. Very good. What was our technique for solving linear equations? Rho equals e to the integral, whatever was right in front of this y right here, which is -1. So that's going to be e to the negative x. And what did we do with that e to the negative x? Multiplied it through. So we're going to have e to the negative x y prime minus e to the negative x y equals x e to the negative x. Now what? You do something. The left-hand side, if you've done everything right, should be the derivative of your integrating factor e to the negative x and the letter y. Let's just see if that works. If I take the derivative, I leave the first one alone. Take the derivative of the second one, that's right. Leave the second one alone, take the derivative of the first one, that's right. Now I integrate both sides, that's correct. So e to the negative x, y is the integral x e to the negative x dx. I use integration by parts, and I'm going to use a tabular method, okay? U and dv. That's going to be x. The derivative of x is 1. The second derivative of x is 0. dv is going to be e to the negative x dx. I integrate once, I get negative e to the negative x. I integrate again, e to the negative x. So e to the negative xy is, I multiply that way, and that one gets a positive. So that's going to be negative x e to the negative x. And then I multiply that way, and that one gets a negative, minus e to the negative x plus c. Or think of that as multiply by e to the x. So y is negative x minus 1 plus c e to the x. Finally, I plug in my initial condition. 1 equals negative 1 minus 1 plus c. Oh wait, that's 0, isn't it?
Yeah.
That one's 0. Plug 0 in for x. So c is 2. So we get y equals negative x minus 1 plus 2 e to the x. So the exact answer should be, if I now want to plug in 1 for x, I should have y equals negative 1 minus 1 plus 2e. How much is negative 1 minus 1 plus 2e?
2e. Or no,
It's negative 2 plus 2e. Somebody grab a calculator. Negative 2 plus 2e. 3.4. Okay. So the exact answer should be about 3.4366. By doing 5 iterations, we had 2.976. How accurate is our answer? Not very good. Still going.
It's very far away too.
Maybe eventually. Yeah, no.
Let's try it again. Let's try 100 steps. So at 100 steps, closer, still not great though, is it?
No.
And you would think 100 steps, it would be better than that, wouldn't you? Brian?
Does it depend on the function, how many steps it takes to get really close to the exact answer?
Yes, of course, it's dependent on the function. It's also dependent on, I started at 0 and I'm ending at 1. If I started at 0 and ended at a half, it wouldn't take as many iterations because they're closer together. If I started at 0 and ended at 20, it would take a lot more iterations because they're a lot further apart. So you begin to see why, even after 100 iterations, Euler might have not been too impressed with his own work.
It's still like 1% off. It's less than 1% off.
Still less than 1% off, that's true. It's not bad.
Yeah,
But remember, Euler didn't have a calculator. And to have to go through that 100 times would have taken quite a while, correct?
Yeah.
Like days, I agree. So, Euler came along and said, well, let's move to section 6.2. So basically we're going to have the same thing. Y prime is going to be some f of x, y. And we're going to have some initial condition, y at x of 0 is y sub 0. All right, so the Euler's improved method. You compute K1. K1 is f at your current x and y value. Then you create this thing called u sub n plus 1. U sub n plus 1 is y sub n plus hk1. That was your answer from Euler's method.
Oh, so you just add on.
So now we're going to correct it. We're going to create this thing called k sub 2. K sub 2 is going to be f at, you're going to have x sub n and u sub n plus 1. And then your next answer, your y sub n plus 1, is going to be y sub n plus 1/2 times k1 plus k2. So basically what we're doing here is, this is the y value that we got from Euler's method. This is kind of the y value you would get from the next step of Euler's original method. And then what's he doing? Averaging them and getting a more accurate answer. So this is called predictor-corrector method. This is your prediction, this is your corrector. High tech. All right, so let's try this one. We'll use the same equation. Y prime equals x plus y. X at 0 is 1. And we still want to know x at 1. 2 steps? You don't want to try 5 again? He learned his lesson, didn't he? And equals 2. Okay, so for this one, we're going to need lots of things. We're going to need n. We're going to need x of n. We're going to need k1, u sub n plus 1, k2, and finally we'll get our y sub n. So if n equals 0, what's x sub n? 0, and what's y sub n? 1. All right.
Will you switch up the chart a little bit?
When n is 1, what's x sub n going to be? 1/2. And when n is 2? 1. All right. So now we've got to start figuring out the k's. So k1 is, I take x0, y0. So to find k1, I take x0, y0, plug it into my function. So k1 is x0 plus y0. So k1 is just 1.
So is there no K1 for that first column then?
No, because for the first column you just have x, n, and y. You just have the original initial conditions. It's for 1 and 2 and 3 and 4, so on and so forth, that you have to figure everything out. Okay, so u sub n plus 1. U sub n plus 1 is going to be my, I'll write it down here, I guess. U sub n plus 1 is my y0. Y0 was 1 plus h was 1/2 And K1 was 1. 3 halves. So I'll read the whole thing so you can see it.
This is a little bit more.
All right, now we got to compute K2. According to the formula, K2 is I take my y sub n, my y sub 0 in this case, and my u that I just figured out, and I plug those back up into my original function. I'm sorry, it's x sub n. I'm sorry, I'm circling the wrong one. X sub n is 0, and then I use this u value for my y number. So that's going to be 0 plus 3 halves, which is also 3 halves.
So are we working with
Who's y?
n equals 1 right now?
Excuse me?
Are we working with n equals 1 right now?
Oh, I made a mistake. This should be x sub n plus 1.
K2.
K2 should have had x of n plus 1. Which means I shouldn't have used 0 here. I should have used a half. I should have used the next x value.
This equals 2.
So that's 2. Okay, so finally, to compute the next y value, I take my original y value, so y sub 1 is going to be y sub 0. Y sub 0 was 1 plus 1/2 times, I add my K1 and my K2. That's 3. So that's going to be 5 halves. So you might notice that was our ending value when we did Euler's original method with n equals 2. We ended up getting that in one step. So our next step is going to be even better, we hope. Okay. So now I got to go back. I got to compute K1 again. So to compute K1, I now use this x value and that y value. So to compute K1, I take x and y and plug them into my original function. My original function was just x plus y. So I'm going to have 1/2 plus 5 halves. 1/2 plus 5 halves is 3.
Can I ask another question?
You may.
If you go down a little bit, so when we did K2, we did 1/2 plus 3 halves.
Yep.
So it shouldn't be x2. So it would be 1.
Well, remember, we're trying to find y sub 1 at this point. So whenever I have x sub n or y sub n, I'm using x sub 0, y sub 0. To find y sub 1, I use x sub 0 and y sub 0. So when this says kn plus 1, up here I'm using x 0, so here I'm going to use x 1. So at this point, when I come down here to find K2, now I'm trying to find Y2. So when I get here, I'm going to use x sub 2. But everywhere else where I just have the x sub n, I'm going to use x sub 1. Okay? All right, so K1 was 3. Now we've got to find u. The u value is our current y value. What's our current y value? 5 halves. Plus h, which is 1/2, times our k1 is 3. So that's going to be 3/2 plus 5/2, that's 8/2, which is a fancy way of saying 4. Okay, now to find k2, I have to use the next x number. The next x number is 1. And then I use the u number that I just found, that's 4. 1 plus 4 is 5. So finally, to find y sub 2, I take my current y value. My current y value is 5/2. I add 1/2 times k1 plus k2. 3 plus 5 is 8. That's 4. 6.5, that seems way too big. Did we make a mistake somewhere? What's that? It's k1 plus k2. Let's see, yeah, it was 1/2.
No, it's 1/2, 8. 1/2 times 8.
Which is 4.
Is 4.
And then 4 plus 2.5 is 6.5.
You screw up on K2?
Did we screw up on K2? Which K2? This one or that one? That one looks right. Yeah, this number's wrong. Alright, so let's check our arithmetic. X sub n, let's see, K1. K1, we use x0 plus y0, that's 1. U sub n plus 1, we're going to have 1 plus 1/2 times that number we just figured out, that's 1. That's 3/2, that one seems right. K2 is, we use this x value, which is 1/2, and then we use that u value, 1/2, 3/2 is 2, that seems right. I don't see a mistake. When you can't be bothered to copy the formulas down right, you don't get the right answers. That was supposed to have a 1/2 h right there.
Oh. Well, we
Don't move.
that should be 1/4 out front.
So that should be a 1/4 out front. So this should have been a
That's pretty how we still got the right answer. Oh, sort of right.
1/4. So that should have been 3/4 plus 1, 1.75. That should have been a 1.75 right there. And then if you do it all over again and you do the right formula, you get 3.28125.
0.5 divided by 2. Why is there still 5?
What's that?
We were missing a half out of there.
Because I forgot this h right here, which added another multiplied by 1/2.
Yeah. So if you take 6.5 and multiply it by half, it's almost.
It's close.
This was way more accurate.
Way more accurate, that's right.
It took us 100 steps to get to.
So that would just be doing 10 steps of the Euler's improved method. We would get 3.428. What was the exact answer supposed to be? 3.4366. So in only doing 10 steps of the Euler's method, I'm closer than, in doing 10 steps of the Euler's improved method, I'm closer than when I did 100 steps of the Euler's regular method. But how many calculations did I have to do that? Well, at each step we have to do 1, 2, 3, 4 calculations, don't we? So if I do 10 iterations, altogether I had to do 40 calculations.
It's still less.
40 calculations is still less than 100 calculations. Significantly less. And my answer turned out to be more accurate. So again, from a computer programming standpoint, this is significantly better. This program runs significantly faster than the other one to get the same degree of accuracy.
And then there's the math.
Harder to do by hand, however. From a computer programming standpoint, much better.